This is Mrs. Palmer-Quay with the third video for Module 12. In this video, I want to talk about the ideal gas law and give you some examples of calculations using this formula. We've been talking about several gas laws in previous videos, and these gas laws describe the relationships between four characteristics of gases: pressure, volume, temperature, and number of moles. So Boyle's law showed us the relationship between pressure and volume, that it was an inverse relationship. If pressure goes up, volume has to go down. Charles's law talked about volume and temperature, where you have a direct relationship. If temperature goes up, volume goes up. And Avogadro's law talks about the relationship between the number of moles of a gas and the volume. Obviously, if you have more moles of a gas, you would have a greater volume because you have more particles. So those three laws are put together to form the ideal gas law. So the ideal gas law shows the relationship between pressure and temperature and volume and number of moles for any ideal gas. There is an ideal gas constant present in the ideal gas law using the letter R, and its value depends on the pressure units. I will always give you the ideal gas constant so that you don't need to worry about memorizing those particular examples. But the ideal gas law is a formula you need to remember, and it states PV equals nRT. Pressure times volume is the same or equals the number of moles times the constant times the temperature. Temperature, remember, needs to be in Kelvin. What's a real gas compared to an ideal gas? Well, an ideal gas follows all the gas laws at every temperature and pressure. That means there's no attractive forces between the particles. Any collisions between particles are perfectly elastic, no energy is lost, and that the particles occupy a zero volume. I think you can see from these standards, especially the last one, that no gas is truly an ideal gas. But real gases tend to behave like ideal gases at high temperatures and low pressures, and so this formula can be used for gases in this state. The graph over here on the right shows the difference between how a real gas behaves when it concerns pressure and volume, and the proposed behavior of an ideal gas. But gases, as I said, at high temperatures and low pressures, like we have here in the hot air balloon, do tend to behave like an ideal gas, and this formula will apply. So to calculate with the ideal gas law, you get a question that will involve pressure and volume and temperature and number of moles. For example, this one asks, what volume is occupied by 3.760 grams of oxygen gas at 88.4 kilopascals and 19 degrees Celsius? Assume that oxygen acts as an ideal gas. The R value for this, given that we have kilopascals, is 8.314 liters times kilopascals divided by Kelvin times moles. When we start off, we've got to do some stoichiometry and convert our grams of oxygen gas into moles. Notice that it is oxygen gas, so this tells us right away we're talking about O2, not just oxygen. So that make sure when you do your calculations with these gases, you are remembering which ones are diatomic and which ones are not. So to start off, to do this conversion, we start with our 3.760 grams, and then we're going to divide that by 32 grams per mole for our oxygen in the O2 state. Those grams per mole, I'm starting to write O2 here. And we'll discover that you have 0.1175 moles of oxygen. So that gives us one figure we need for our ideal gas law. The other thing is we've got to change this Celsius into Kelvin. So we have to take our 19 degrees Celsius and add 273 degrees to it to give us our final answer of 292 Kelvin, so that we have the correct temperature, because temperatures are always in Kelvin. So then we just have our PV equals nRT, our ideal gas formula. We want to rearrange that to solve for volume because the question's asking about volume. So volume is going to equal nRT divided by P. And now it's just a plug and chug. Take all the information we have. What's N? 0.1175 moles. What's our R? I gave that to you, 8.314 liters times kilopascals divided by Kelvin times mole. So we've got some units that have to be canceled out here. And then the last thing in the numerator would be our temperature, which was 292 Kelvin. We divide that whole shebang by the pressure, which has been given to us in kilopascals, 88.4 kilopascals. And when you go ahead and do all the math and cancel out all of the units, I'm kind of running out of room here, but your answer will be 3.23 liters. And so the 3.760 grams of oxygen gas at the conditions described in this question will occupy a little bit over 3 liters of volume. So basically, with using the ideal gas law, the most important thing is to remember to change your temperatures from Celsius into Kelvin and to make sure you've got everything in the correct units. Other than that, it's pretty straightforward. This problem asks you to do a little more stoichiometry. It says what volume of carbon dioxide is produced by the combustion of 25.21 grams of ethanol, C2H5OH, at 54 degrees Celsius and 728 millimeters of mercury. And I give you your constant for millimeters of mercury. So we want to start off by writing a balanced equation because we've been given ethanol, but we're asked to find out about carbon dioxide. So we're going to have to look at mole ratios in order to complete this problem. So we're going to take our ethanol and we're going to react that with oxygen because, of course, combustion asks you to react things with oxygen, and you get as a result carbon dioxide and water. This skeleton equation is not balanced. Some coefficients need to be added. We need to add 3 in front of oxygen, 2 in front of carbon dioxide, and then 3 water. And so then we can see that our mole ratio for every mole of ethanol, we're going to produce 2 moles of carbon dioxide. So we need to remember that because we're going to need that in a minute. The next thing to do is figure out how many moles of carbon dioxide will be produced. So if we have our 25.21 grams of the ethanol, and we divide that by how many grams are in a mole, 46.08 grams per mole for ethanol, and then we can multiply that by our ratio of 2 moles of carbon dioxide for each mole of the methanol, or ethanol, sorry. So I'll just put F here. And we go ahead and multiply that out. You will find that you are going to produce 1.094 moles of carbon dioxide. So we've used stoichiometry and our balanced chemical equation to figure out the number of moles of carbon dioxide. Now our question asks us for volume of carbon dioxide, so we have to go back to our PV equals nRT, our ideal gas equation. We're going to rearrange that so that volume is what we're solving for by dividing by pressure. So we just get rid of this one over here, and then we just plug in. So we're going to plug in the amount of moles for N. We figured that out. It's 1.094 moles for our carbon dioxide. We're going to put in our R, which I have given you as 63.36 liters times millimeters of mercury, divided by Kelvin times mole. Again, this is to cancel out all of your units. And then the last thing here is temperature. And so we're going to have to convert our 54 degrees Celsius by adding 273 degrees to Kelvin, and the end result there is 327 Kelvin. And we divide all of that by the pressure, which is given to us as 728 millimeters of mercury. And so when you go through and do all of the math, after you have this set up, you will find that the answer is you're going to produce 30.6 liters of carbon dioxide. So problems involving the ideal gas may require you to go back and draw upon those techniques for stoichiometry that we've not done for a couple of modules, but hopefully they're still there in your brain somewhere. So this finishes what I want to say for this third video for Module 12.